let's jump into two examples on specific heat capacity. So these two examples relate back, and the assumption is that you are familiar with specific heat capacity, at least with the actual formula for it. I can put up a link up above there where I get into kind of the smaller details and introduction to specific heat capacity. And here I'm just going to take a look at two examples. So here's the first example. So during a procedure, a gold instrument has been used. The specific heat capacity of gold is actually rather small, so it's a pretty good conductor, and it's 129 joules per kilogram per degree Celsius. All right, so let's write that down in our given pieces of information. So our specific heat capacity is 129 joules, and this is per kilogram per degree Celsius. So the instrument's temperature has gone up by 3.2 degrees Celsius. So that means that's the change in temperature, and this is 3.2 degrees Celsius. The heat transfer amounted to 252 joules. So that would have been our Q. So that's the amount of energy that has been transferred, and that will be 252 joules. What was the mass? And that's what we're going to be looking for of the instrument. So if you take a look at the actual formula there, so indeed, so we do have Q, so that's the left hand side, so let's write that all out. So there's going to be 252 equals. We don't have our mass, M, so that's what's missing. We do have our specific heat capacity, so that's 129 joules. Now we do have to be careful here so that all the units are aligning. So notice that you have, this is joules, okay? So this is in joules, so that's fine. And this is in degrees Celsius, and this is in degrees Celsius. So all of that is okay. So the only thing that we are missing there is going to be this kilograms, and that's going to be the mass that we're going to obtain. So coming back, okay, so that is, units are all consistent, so that's fine. And now substituting at the end, so that's going to be the change in temperature, so which is 3.2. So I'm going to drop all of the units, and I can solve for our M. So our M is going to be equal to, so it's going to be 252, and then I can divide both sides by 129 multiplied by 3.2. So, okay, so these two items I can divide by on both sides, and I'm going to get my M. So what is M? So M is equal to, so now if I take out our calculator, so divided by, so 129 and 3.2. Notice I'm just putting it all in brackets there, and that's going to be 0.61, and this is going to be in kilograms. All right, so that's it. Now I just kept it to two significant figures because that's the smallest amount of sig figs that I have. Okay, so that's on the rounding side, and of course, if it doesn't tell you to round, just round to the smallest number of significant figures. And I can put up a link up above there on the rounding on sig figs if you ever forget. So this is this example. So it's not bad. It utilizes the actual formula directly. Here is a second example. So this one looks like it's a little bit longer. All right, so let's take a look here. So an aluminum medical instrument is to be cooled by placing it inside 350 milliliters of water. So maybe I'm going to just write this down for myself here. So we have aluminum, okay, and then water. Now water, so the mass, now please recall, so 1 milliliter you can always assume is about 1 gram of water. So that means, okay, so my mass of water, so H2O, is going to be 350 grams in there. Now 350 grams is the same thing as 0.35 kilograms, okay? So depending on what we will need, I'll just leave those two. All right, so that's our water there. It has been noticed that when the instrument gets placed in water, the temperature of the water increases by 1.5 degrees Celsius. All right, so that's the change in temperature of the water. All right, so in this case it increases. So it's going to be positive 1.5 degrees Celsius. while the instrument decreases by 65 degrees Celsius. All right, so that's interesting. So that means the change, and this is going to be in the aluminum, okay, right there. And that's going to be 65 degrees Celsius. All right, so that's a big drop there. Okay, so that's the second item. Now, I'm going to just separate this again. You don't have to separate it. I just want to kind of break it down because here we have mass, here we have the change in temperatures. Now, moving forward, it says, by looking at a table, you notice that the water and aluminum have specific heat capacities. And so they give those to us. Okay, so that's right there. And it's 4,184 and 898 respectively. And yeah, so it's, you should be familiar more and more as you do the questions. Water is about 4184. So I can write those down. So let's put that information in here. So that's going to now give me specific heat capacity of water, and this is 4184. Actually, the unit's on the next line. Okay, so the unit is joules per kilogram per Kelvin. So this is joules, okay, per kilogram. Now it's per Kelvin. Now, don't forget that the change, so if you're changing it, okay, Kelvin, okay, the change in Kelvin is basically the same change as in degrees Celsius, because Kelvin is just shifted by 273. Okay, so you can recall that from temperature, and I can maybe put up a link up above there, okay, if you want to get back into going back and forth between, okay, Kelvin and degrees Celsius. But the nice thing is that the change in Kelvin is the same thing as the change in degrees Celsius. So therefore, I'm going to just put degrees Celsius, and the reason for that is because it's just going to be consistent with the lines above there for the change in temperature. All right, so that's that. And then my aluminum right there, and this one was 898. All right, so this is joules, kilogram, degrees Celsius. Okay, so now find the mass, okay, of the lead. Okay, so it's not going to be lead. I guess this is aluminum, so it's a typo. Okay, find the mass of the aluminum instrument from the given information. So assume that none of the heat escapes to external sources. Okay, so that's fine. So if nothing is escaping, so this will now bring us back to, okay, this heat transfers back and forth, and also the law of conservation. So what that means is that the heat transfer, okay, of the water plus, okay, the heat, now this is going to be whatever this is absorbed, right? So the water absorbs, and since it's absorbed, the temperature has increased, and that's what we have seen here. Now the aluminum, okay, has decreased. So technically, so this, I'm going to put a negative because it has dropped in temperature. Okay, so that is for the aluminum, and this is what it has released. And because nothing is escaping to anywhere else, okay, to any external sources, so that means, okay, by the law of conservation, okay, this is going to be equal. Okay, so that means it's just an exchange between one and the other. And therefore, so what we will have, I'm going to just write this as Q, H2O, is going to be equal to the negative of Q of the aluminum, okay, whatever has been released. Okay, so that's what we know. Now we're trying to find the mass. We don't have the mass of the aluminum, and that's exactly what we're trying to find here. And you can see there from the givens, we don't have it. Now, if I take this line, so don't forget, this is nothing else but the mass of the water, right, times the specific heat capacity of the water, okay, times the change in temperature of the water, right? So that's my Q. And if the transfers of energies, okay, are such that one goes towards the other, then the opposite, right, so it's going to be negative. I'm going to put all of this in brackets. It's going to be the mass of the aluminum, which we do not know, multiplied by the specific heat capacity of the aluminum, and then the change in temperature of the aluminum. And now I can take all of these and then substitute them back in. Please notice, so here, okay, this is per kilogram, right? So this is the specific heat capacity per kilogram. So I'm not going to use grams, okay? I'm actually going to use kilograms as my mass for water, just so that I'm consistent, okay, with the specific heat capacity. So if I go back in here, so this is what I'm going to have. So this is going to be 0.35 times 4184, this is joules per kilogram, okay, per degree Celsius, okay, and then times the change in the actual temperatures, which is going to be 1.5 degrees Celsius, okay. So on the left hand side, I basically would have just joules. Now on the right hand side, so this is negative, okay, and then in brackets. Now I don't know what this is, at least not yet, but I'm going to be able to solve for this. Okay, this is going to be times 898, so notice joules per kilogram per degree Celsius, times, now here I have to substitute the negative, right, because it drops in temperature. So it's going to be negative 65. And as soon as I write that in, you know, you could see there that this negative and this negative will just cancel. So that means the two heats, so the heat transfers should be identical. And now this is nothing else but simply just solving, okay, for this mass of the aluminum. So you can divide now both sides by the 895 and the 65, and you're going to get exactly what you wanted, which is going to be the mass. All right, so here, now all of this, okay, maybe let me just work this out. So I'm going to just take this out, 0.35 multiplied by 4184 times 1.5. So that's going to be 2196.6. This is all joules. This is going to be divided by now, I'm going to keep this on the calculator, divided by 898. Okay, so that gets rid of this right here. Okay, divide by both sides. So that's gone. All right, so let's take our answer divided by 898. So that's the first one. And then also divide by the temperature. All right, so divided by the temperature there, so that's 65. So answer divided by 65. And now, okay, we're going to get exactly, okay, what we wanted there. So it's going to be the mass, okay, aluminum, and it's 0.0376, etc. Okay, that's going to be kilograms. Okay, which is about, okay, if you want to change it back, so about 30, well, let's round it, 38 grams. All right, that would have been the mass. Now, if they want it in kilograms, you can leave it in kilograms. You don't have to. So this one is in kilograms. This is in grams. Okay, so it's times 1,000, right? And I kept two significant figures there. So there you have it. So that's how you would be able to kind of go through this process. So it's another question, okay, on this specific heat capacity, and it's kind of nice because it allows us to see the transfer of energy. So one absorbs and one releases it, so obviously their temperatures change. One temperature increases, the other temperature drops. And that's actually very common, okay, thing to do. You know, sometimes if I'm drilling, okay, and you know, as the drill bits, okay, are going to be typically made out of some metal. And then they get hot really quickly, okay, as you're drilling, because there's just so much friction. So that particular friction that you have is going to be increasing the temperature of your drill bit. And you know what I do is I have water, and I actually literally just put it in water so that it starts to absorb it. Okay, and because of the fact that water has such a high specific heat capacity, meaning that you need quite a lot of energy, right, to be able to increase its temperature, you know, you can cool the bit, okay, rather quickly. And this is kind of how this instrument has worked. So probably this is what was happening, okay, within this. So maybe it was a bit, okay, so made out of aluminum, and then it's been used for something, okay. If it's medical, I don't know, maybe surgery. All right, so thanks for watching. These are the two examples. I hope that you have found them useful and you understood them. Okay, we'll see you in a future video. Bye, everybody.